presented by Caltech.
Hello, everyone, and welcome. I'm so glad to see so many of you here. Can everyone hear me? Excellent. All right. My name is Julia Greer, and I'm a Mettler Chair Professor of all things that begin with an M, so material science, mechanical, actually not mechanical engineering, mechanics, and medical engineering. And you'll see that this M theme actually runs through the presenter today as well. And I'm also the Fletcher Jones Foundation Director of the Kavli Nanoscience Institute, which is why I have the honor of introducing our KNI-Wheatley Scholar, Professor Mohammad Mirhosseini. Notice the M theme again. This is a very special lecture of the KNI-Wheatley Scholar, which was established by Dr. Chuck Wheatley, who is sitting right here, and his late wife, Judy, in 2016. And so we have two distinguished alumni. I just want to start with this today. So we have Mohammad and Dr. Chuck Wheatley here. Mohammad's research is focused on entangling distant transmon qubits. Did all understand what that meant? Via microwave waveguides and integrated microwave to optical transducers. Mohammad is also a former KNI Prize postdoc scholar at Caltech, and before then he was working on his PhD at the University of Rochester, which is very well known for its Institute for Optics. His work has been recognized by many awards, including the Best Thesis Award, as well as some of the most notable national recognitions like the NSF Career Award and the Young Investigator from the Air Force Office for Scientific Research. Today's lecture is supported by the KNI-Wheatley Scholarship in Nanoscience, and it's specifically aimed to support these brilliant early career scientists. We only have brilliant people here at Caltech. So this is a big honor and a recognition for Professor Mirhosseini as well. So with that, I'd like to extend a special thank you to the alumni relations team who's really helped us highlight this lecture here today and to also co-organize this event as part of the overall alumni weekend at Caltech. And so on behalf of the Kavli Nanoscience Institute, I'm delighted to celebrate both of these Caltech alums. So with that, please help me welcome Professor Mohammad Mirhosseini, and thank you very much, Chuck, for your unwavering support of the KNI. Thank you.
Hi, everyone. Thank you, Julia, for the introduction, and thanks to the Kavli Nanoscience Institute's board for selecting me for this scholarship. It's indeed great to be here today. So I'm going to talk about transferring quantum states between different locations and different physical systems. But before I tell you about that, I have to tell you why do we want to connect quantum systems and what are the quantum systems in the first place. So to do that, let me get started by talking about this field a little bit in general. If you follow science and technology news, you are probably already familiar with some of the recent developments in this area. If we follow the recent developments, we have a group of activities that are aimed at making a computer operating based on the principles of quantum mechanics. And in parallel, there's another set of activities aiming to send quantum states over long distances using quantum mechanical objects. So we can collectively perhaps call these as quantum technologies. These type of systems, of course, rely on physical principles that we know for a long time. Quantum physics was developed more than a century ago as an attempt to understand the physical universe at the very smallest scales, where everything is made from small particles. The most well-known examples of these particles are atoms, the building blocks of matter, and photons, the particles of light. And the first steps to understand these particles and the way they interact with each other was put forth by Max Planck, Niels Bohr, and Albert Einstein, and then expanded by other people to a full theory, and that's what we call quantum mechanics today. Perhaps the most important feature of quantum physics, before even trying to talk about its detail, is that everything here are described in terms of discrete quanta. The most famous example is the energy. Consider a pulse of electromagnetic waves or light. Quantum mechanics basically tells us that the energy in this pulse is divisible to small units, which we call photons, the particles of light. The energy of these units is proportional to a constant multiplied by the frequency of the light field. But once you have this unit, you can only make integer multiples of it in a pulse. Energy is not the only discrete variables. There's other discrete variables as well. Another well-known example is the spin of an electron, which is a property related to the magnetic properties of an electron. And you can somewhat understand it as an electron spinning or rotating around an axis. Here, quantum mechanics tells us that the rotation axis can point up or down, but no other direction. So again, we have a discrete variable where in this case can only take only two values. Now, I mentioned technologies. I have to say that quantum mechanics already has had profound impacts on the technological aspects of our lives. These are a few examples of systems that rely on quantum mechanical principles, semiconductor lasers and MRI machines. In fact, it's very hard to avoid quantum mechanics. If you try to make something, it's ultimately the theory that describes matter and light. So we would need it for most things. However, these examples in these things, usually we are dealing with systems of many particles. And in some sense, we are always interested in some average properties of these particles. Whereas in some of the more recent things that I showed you, like quantum computers, we are trying to measure and control the quantum properties of each and every particle in a system that it still has many, many particles, which sounds like a more difficult task. The reason for trying to do this difficult task is to make use of some of the more exotic features of the quantum physics. And to explain it, let me tell you a little bit more about measurements. So quantum mechanics actually does not allow us to predict the outcome of a measurement completely, which sounds a little bit odd. What it does instead is tells us the probability of events happening. So think of this example of the spin that I mentioned earlier. Here there is two outcomes, up or down. Quantum mechanics tells us to make a mathematical construct, which we call a quantum state. In this simple case, this state has only two numbers in it, shown by these letters, psi1 and psi2. We can take these numbers and we can actually do some math, in this case take the square of their modulus and calculate the probability of events. So in a sense, doing a measurement like on a spin is like spinning a coin. If you flip a coin, they get up or down, heads or tails. There's a binary outcome. You can know the probabilities, but you cannot predict each and every measurement that you will do. This is a rather undesirable property and has been much debated. But if you ignore the more conceptual aspect and focus on doing calculation, seems like it's relatively straightforward. Calculate these vectors that we call the quantum states, and from that back out the probabilities. However, even trying to do this in practice faces some challenges, and that is because if you have a larger system, these vector tends to become very large, basically. So think of an example of a system with multiple electrons. If you have multiple spins, if you have n of these, then the size of these vector becomes 2 to the power of n, and that's a number that grows very rapidly. So even if you have something like 300 electrons, which is a modest-sized system, the size of this vector becomes a number that is larger than the total number of particles in the entire universe. So it sounds like if you want to do any type of numerical calculation using a conventional computer, you'll have a difficult job. This is even worse when you try to look at the evolution of a system. You have to take these large vectors and multiply it by even larger matrices, and it is still is a very difficult task. So given this complexity to predict the behavior of quantum systems, one can perhaps ask a question that if we have a quantum system, can we design it such that its evolution in time maps to a mathematical problem that we want to solve? If you can do it, maybe you can let the system evolve in time and then somehow find the quantum states or properties relating to it, and you find the answer to your mathematical question. And if it is possible, perhaps these quantum systems can actually do it faster than the classical system, like the conventional computers that we use in everyday life. We are talking at Caltech, so it's very hard to not mention Richard Feynman, and he's in fact one of the first people who is credited with this idea of using quantum systems for computation. So the answer to this question is basically yes. Over the past decades, people have looked at many problems, and now we know a few problems that can, in principle, run much faster on a quantum computer, to the extent that we can call these problems practically unsolvable on a traditional or standard computer and only solvable on a quantum computer. Before talking more about quantum computers, I want to make 2 points. One of them is that this computational advantage is only for some problems, not everything. So even if we have a quantum computers, we cannot feed it any problem we desire and let it solve it for us faster. This is something that somewhat limits the applicability of these machines, but still, we know of certain problems that have a very wide range of application problems that are related to cryptography, material design, and optimization. The second point is related to this statistical or probabilistic nature of quantum systems. I mentioned this quantum state that gives us the probabilities, but the entities in these quantum states are not probability itself. You have to take this modulus square to calculate the probabilities. This is a very subtle distinction, but it has profound actually results if you think about it. In systems of many particles, you can run into very surprising results because of this distinction. And a well-known example is a phenomenon that we call as quantum entanglement. It's a situation in a system of two particles where if you look at one of the particles and you try to do a measurement on it, the outcome of your measurement would be very strongly dependent on what you see on the other part, as if these two particles are somehow linked together. I will not talk about quantum entanglement much and what it is, but I want to mention that quantum entanglement is an essential part of quantum computing. And in fact, going beyond computation, we know of other operations such as communication and sensing of weak signal that can benefit from quantum entanglement. So when referring to quantum technologies very loosely, we are talking about operations or tasks that can benefit from quantum entanglement. Okay, so I hope this very brief overview of quantum computation gives you some idea of what I want to talk about. Next, I want to focus about building these systems. I used spin as an example of a very simple quantum system that has only two possible states or two possible outcomes if you do a measurement on it. In the language of quantum computing, we call anything that has this binary outcome a qubit or a quantum bit. The idea is that these qubits are the building blocks for processing and storing quantum information in the same way that bits are to a regular computer. Now, it's rather difficult to make a qubit in practice. You need a system that you can isolate well from the environment. It's because interactions with the environment change quantum states in undesired and unpredictable ways, and that's something you want to avoid. But you can imagine that at the same time, you want to be able to change these quantum states and measure them. So these are rather complementary features that are hard to bring together in a system. So over the past decades, there has been a lot of progress in attempting to make systems of multiple qubits. This is a very incomplete graph that I made a while back that shows some of the progress in this field. So this axis is the time in year, and this is the log scale showing the very rough estimate of the number of things that we can perhaps call qubits in experiments. And as you can see, there has been a lot of progress. We could only control 1 or 2 qubits 20 plus some years ago, whereas today we can work with systems that have hundreds of qubits. This is a big progress, but I have to say that solving these quantum problems or running what we call quantum algorithms still requires a much, much larger system. So there is a long way left to go, but still we have now some small-sized processors that we can try our ideas on at the moment. Thinking a little bit about the hardware aspect, okay, how do you make these things? There is multiple platforms for making qubits. One of the platforms that has had a lot of success and some of the recent results are based on is called superconducting qubits. These are electrical devices that are actually rather large. They are not single particles, unlike these examples that I gave you. So these are electrical entities that have energy stored in charge and current, much like our conventional circuits. However, they are made from superconductors, which gives them a very low energy loss, and that allows us to access discrete energy levels, and that is basically one of the things we need to make a qubit. I will not talk about the details of what these things are. This is some picture that gives you a sense of them, how they look. They are built from superconducting metals on dielectric substrate, and you can make them using microfabrication technology in a rather similar way that compared to what we do for making the conventional semiconductor devices. And this is part of their appeal. You can, in principle, make many of these on a chip, and perhaps you can use it to make a quantum computer. So we have some candidate system to make qubits, but beyond qubits, we also need to do more operations in a quantum computer. In fact, going even beyond computation and thinking about communication and sensing, any experiment really can be boiled down to some basic operations. We need a place to store quantum information or quantum states and modify them. And we need a way of sending quantum state or quantum information from one location to the other, which means that we need some sort of an interconnect. Now, superconducting qubits do a good job when it comes to storing and processing quantum information. But when it comes to transferring quantum states, things are a little bit more tricky. In the classical world, if we want to send information from one place to another, what we do is we essentially record our message or our signal. We reproduce it then in whatever medium that is best, and then we send it over some link to another party. In the quantum world, if you want to send a quantum state from one location to the other, there is no way to either measure or make a copy of this quantum state. So the only thing you can do is to physically load it to a qubit and let the qubit propagate from point A to point B to do communication. This makes it very hard to make these interconnects. For example, these circuits that I showed you are stationary objects. You cannot send them over a link. So you need another way to communicate information between 2 points. Fortunately, things are not as bad as I made it sound like. If you think about electromagnetic waves, we know that they propagate rapidly. I also told you that photons give us discrete variables. They have discrete energy levels. So you can take a pulse of electromagnetic radiation, and then you can put either 0 photon in it or 1 photon. That gives you 2 possibilities. And using this, you can define a qubit. But this is a qubit now that propagates or fly, and using these flying qubits, you can now make a quantum interconnect. So at the end, the communication aspect is very similar to the classical system. The only difference is that we can have at most only 1 photon in every signal packet that we send. And we have to make sure that that photon makes it to the destination. Superconducting qubits naturally emit photons. These are electrical circuits, and you can make them like tiny antennas. And using that, you can actually have the qubit emit its quantum state in form of a photon and use that photon. The photon will be in what we call as microwave spectrum. It would be in a few gigahertz frequency. But you can, and then you can capture it and put it in a cable to send it from one location to another. However, I mentioned that the energy of a photon is related to its frequency. So if your photons have very small frequencies, like a few gigahertz, their energy is very small. That means that these packets of information or states that you try to transmit over a channel will be very sensitive to any noise in the system. There are many types of noise that you may care about, but there are some types that are unavoidable. And one example is the emission from thermal objects, the objects that are not at 0 temperature. So to do communication with these systems, you need to essentially cool down everything very close to absolute 0 to be able to send the quantum state in microwave photons. That sounds like a very difficult task, but It's not impossible to do. These qubits are based on superconductors, and we have to use cold environment to work with them anyway. So if you're talking about short distance propagation, you can use the cable and you're fine. However, if you want to go a little bit longer distance, things become much more difficult. This is a beautiful experiment that shows an attempt to send quantum states from one location to another over a cold tunnel where you can place cables in it, and it works fine. But you can imagine that if you go to larger distances or if you have many cables, things become quickly very difficult. So our idea in solving this problem has been to use a different approach. If instead of these microwave photons, we use optical photon of the type that we can see with our eyes or frequencies near there, to transmit information, the energy of the photon would be very large, which makes it very robust against noise. In fact, with visible photons, we can send quantum states in room temperature without worrying about thermal noise at all. Besides, optical photons propagate over long distances in optical fibers, so that really helps us in making very long distance links. This is an idea, I have to say, that we use in the classical world in data centers and communication nodes. Optical fibers are used for transmitting long distance information, but we move information from the optical domain to the electrical domain to do computation on our computers. So even though we don't fully understand how a quantum system will look like and how it would affect technology, chances are we would need something similar, a transceiver, to convert information from the microwave domain to the optical domain. So this is basically one of the things we try to do. But how do you do it? In order to convert a microwave photon to an optical photon, you have to take a photon and increase its frequency, essentially. We are talking about a very large frequency gap from a few gigahertz to hundreds of terahertz, so it won't be easy. Besides, you would have to have a process that works for very weak signals, so you have to be very careful about noise and efficiency and other technical considerations. In terms of how to do it, this process of increasing frequency is equivalent to destroying a photon at low frequency and at the same time creating a higher frequency photon. And this is what we call as a type of interaction between photons. Unfortunately, interaction between photons is not permitted in nature, in vacuum or in free space. So there is no direct way to do this. However, photons interact with material particles or with matter. So if you have a system, a material system that interacts with both microwave and optical photon, you can indirectly do this conversion process to go from microwave to the material particles and from there to optical photons. Now, part of the work in our community is trying to find good candidates for this quantum bridge, this intermediary system. What we work on is actually mechanical vibrations that quantum mechanically we can describe mechanical vibration as particles called phonons. It might sound like an unusual choice for this purpose, but I will try to convince you that this is not such a bad idea. Mechanical vibration actually interact with optical light via a process known as the Doppler effect. You are probably familiar with the acoustic analog of this, where a car or a vehicle moving with a loud siren, when you hear the sound from it, you hear the pitch of the sound changing drastically as it goes by. There is a similar effect for light. If you shine light on a moving mirror, the reflected light will experience a slight frequency shift. So if you block the light that you send at the original frequency and you only look for the frequency shift, then you can actually detect mechanical motion by just looking at light. So quantum mechanically, this is just conversion of optical photons to phonons and vice versa. This is, of course, a very weak effect, so it's not easy to do it, but you can play tricks. You can make a cavity where you force light to go many, many rounds in a system and continuously interact with the moving part. And you can also try to make the system very small, making it very sensitive to a small vibration. And these things collectively allow you to detect a single phonon by converting it to a single photon, the way that I described. This line of work is called cavity optomechanics, and it has a very rich history at Caltech. These are some images of some of the devices made by Kerry Vahala group and Oscar Pinter's group in the past. Okay, so I hope I convinced you that light interacts with mechanical vibrations. But what about the electrical signal? Well, to get interaction between electrical signal and mechanical motion, we can use material properties, namely piezoelectricity. In piezoelectric materials, if we put a force on an object and make it deform, we can make it accumulate charge on its sides, or we can actually use this process in reverse. We can inject charge into a block of a piezoelectric material, and the charge would make it deform. This is widely used in the classical world. A famous example is a quartz oscillator, which is used in every watch, and it's a relatively well understood process. So if you put these things together, at least conceptually, you have a recipe for converting microwaves to light. You should start with something like a superconducting qubit, take some electrode to move the energy to mechanical oscillation in a piezoelectric block, somehow send the mechanical vibrations to an optomechanical cavity, and there you can come in with a laser light and read out these vibrations. There's, of course, many technical challenges. I won't tell about all of them, but I will give you a few things to give you a flavor. The first thing is you have to define your optomechanical device and the piezoelectric section. Without going into too much details, I will just mention that by patterning structures at nanoscale, we can make confined mechanical vibration. We can also play the same trick to confine optical energy. So we can actually make a device where mechanical vibration live together with optical photons in a shared volume. For piezoelectric devices, we essentially need a pair of electrodes and a section of a piezoelectric material. We can again make geometric patterns which are periodic, and that allows us to confine mechanical motion. This is a picture of movement into a piezoelectric section. This raised the slab over here, and as you can see, we have a confined mechanical mode. So I mentioned you have to connect these things together. This is an example of a device. We have these extended mechanical modes now living in a piezoelectric section and an optomechanical section. If you electrically drive this system at the right frequency, you can get this distributed energy, and then if you come in with a laser light, you can read out the photons on the other side. Now, to make this device, of course, you have to do a lot of work. I will not go to the details again, but essentially you have multiple steps of material deposition and selective removal to make patterns you desire. I also mentioned that we have to make freestanding structures. So one of the tasks is to remove the material underneath our structures to make a membrane where things can freely move. So this is an example of the image for a device made based on this concept. Here you can see the piezoelectric section with these electrodes in false color on top of it. We have this beam where our optical mode lives. And then next to this beam, we have another beam-like structure, which is actually a waveguide used for sending photons into this cavity and reading it out. Now, once you make this transducer, you have to attach it to a superconducting qubit. This is the outline of a full system. You have the transducer device over here, and it's attached to electrodes. You can follow these electrodes. They come out, and they're attached to a superconducting qubit. On the other side, we have an optical cavity, which we can use to address this system. So once you make something like this, you have to cool it down to low temperatures. I mentioned we want to make these optical photons because we can take them to room temperatures, but the process of conversion itself has to happen at cold. For that, we need cryogenic systems, but we know how to do this. And then finally, if you have everything, you can try to do an experiment. The experiment conceptually follows closely what I told you before. You start with the qubit. You can control the frequency of a qubit, so you can force it to go to the same frequency as your mechanical mode. There you move energy to mechanical vibration. And once you have the mechanical vibration, you can read it out with a laser. This is an example of an experiment based on this concept. The violet bar over here shows the measurements of the system if you excite your qubit with an electrical drive. And as you can see, we get a large signal. If you repeat this experiment without driving your qubit, you get this red bar over here. This is the case of qubit being in the lower energy level. This is the case of qubit in the higher energy level. You ideally expect to have nothing when the qubit is in the low level, but of course we get something because there is some noise in any realistic experiment. But basically we can convert the signal to noise ratio for a signal that is only 1 photon large. And as you see, this signal to noise ratio goes slightly above 1, which tells us that we are at a point that we can barely do operations on quantum states. This is a more interesting example, perhaps. Here we start with a qubit. We electrically drive it. The qubit is initially in the lower energy level. Once you drive it, you put the population from the lower energy level into the upper one. Now, this is the result of an optical measurement where we look at the optical photons coming out. And as you can see, the chance of detecting a photon increases as the function of the duration of drive for a while. But the two-level system cannot take energy forever. So if you try to feed energy to it more and more, it actually starts going down. The population goes back to the ground state. And if you continue doing it, you get an oscillation. This type of oscillatory behavior is called Rabi oscillation. This is actually a signature of a qubit that you look for. Now, with these type of optical interconnects, we can actually measure these things directly by looking only at the optical photons, which is, again, a verification of what is possible with this type of interconnects. Now, more recent work in this community is aimed at finding the bottlenecks in this process and make it work faster and more efficient. In my group, we have been focused on looking at the decoherence of the mechanical waves, which is one of the factors affecting these type of interconnects. Without going to details, I'll just mention that we have recently found a way to actuate mechanical modes without needing piezoelectric materials, which gives us a lot of freedom in fabricating devices out of materials we know better. And this has paid off in finding materials with lower mechanical decoherence. We, in fact, made a device and measured it recently out of silicon, which is a well-known material that is easy to work with. And we learned that the rate of energy loss in the mechanical modes is far lower than some of our previous experiments with a variety of materials, which is a very promising thing, telling us that we can potentially now make transducers with far better signal-to-noise ratios. Now, taking a step back, I just showed you a device and what it can do in the relatively short time that we have. The bigger picture is that if we can use these transducers to distribute quantum entanglement between multiple nodes, then we can go ahead and build a general-purpose quantum network. If we can do this, we can imagine using these type of network to connect small processors of superconducting qubits to make a larger quantum computer, or we could actually use these type of system to provide remote access to a superconducting computer that is located at a distant location. This second point is interesting because there's actually a way of providing secure access to a quantum computer where you load your mathematical problem of interest remotely to the computer in a way that you make sure no third party can access the details of the problem you want to solve, and then you securely read the answer, again, without a third party or even the quantum computer itself knowing what it is solving. And some of these ideas are not so far ahead if we make some more progress in making these transducers. I have to mention that I focused so far mostly on qubits and interconnects, but I did mention that we also need a way to store quantum information. That brings us to something else we call as quantum memories. In the superconducting qubits, with the superconducting qubit system, currently the best way to store quantum information for a long time is what we call an electromagnetic cavity. these are large devices. As you can see, they are centimeters in size. One of the side benefits of the research we have been doing has been learning about mechanical systems more, and we have been reducing their decoherence, as I mentioned. One nice thing about mechanical oscillators is their small size. The size of a mechanical oscillator is typically a few microns at a frequency of a few gigahertz. So if we can control this system well in the quantum regime, we can actually think about using tiny mechanical oscillators as quantum memories. I should also say a few words about electrical interconnects. Interestingly, I cannot see one of my pictures here. It's OK. I think I've had many so far. I focused on optical interconnects when talking about long-distance communication. And I told you that for short distances and low temperature, things are by and large fine. However, in the short distance, even though we can use an all-electrical system to send information, we still have a lot of need for better connectivity, basically because we are aiming to make very large and sophisticated systems. So recently, we have been able to make a new type of interface between superconducting qubits and microwave photons, which allows us to have a photon propagate only from left to right and not the other way around, which sounds something very simple, but it's actually non-trivial to do. And with this type of interfaces, we can actually now think about doing more complicated operations with these electrical systems. We can, for example, imagine taking a number of qubits and linking them all with a single wire, and then distribute entanglement between pairs of qubits or between even multiple qubits using this interface that I mentioned. And entanglement distribution is the main building block for doing any quantum operation. So in some sense, we are enabling what comes next. Finally, I have to say that everything I said was focused on the technology aspects. How do we make this system? How do we make them larger? What can we do with them? But one of the side benefits of this type of research is that we are getting more control over individual quantum systems. For example, these superconducting qubits emitting microwave photons essentially work like an artificial atom that has an emission band in the microwave spectrum. Being artificial entities, we can engineer many of their properties, including their frequencies, their rate of emissions. Similarly, with photons, we can change their shape or their speed of propagation very easily. So this gives us a system in which we can study light-matter interaction in regimes that are not easy to reach with natural atoms and optical photons, and that is another thing we are interested in and are working on actively. So this concludes my talk. I should thank the hard work and the innovation from all my past and present members of my group who are listed over here. We have also had the privilege of working with many people at Caltech, JPL, and elsewhere, especially Oscar Painter's group, where I was previously a postdoc. I also take this chance to extend a deep thanks to Dr. Chuck Wheatley and his late wife for their support of the KNI-Wheatley Scholarship, and the Kavli Foundation for supporting the cleanroom facility and the Kavli Nanoscience Institute on campus. Also, we are very grateful to all the funding agencies who support our work. I would be happy to answer any question. Thank you for your attention.
Can you give a little more information about an example of a problem that a quantum computer could solve?
Perhaps the most famous, so the question is, what is a good example of a problem that a quantum computer can efficiently solve? The most famous example, perhaps, is the problem of factorizing a number to prime numbers. Take 15, decompose it to 3 times 5. That sounds like an easy problem, but for very large numbers, it turns out that this factoring becomes exceedingly hard. In fact, the difficulty of these decomposition is the basis of some of the conventional cryptography systems. It's very hard to do this factorization. And this has been shown many years ago now that can be done on a quantum computer in a fundamentally much faster way compared to a classical computer. So hence the implications for cryptography that I mentioned in my slides.
Doing things like modeling climate, is that outside of the scope?
The question is if modeling climate or similar problems is outside the scope. Well, I have to first mention that I think one of the purposes of my talk was to mention that I'm the cable guy of the quantum world, not the software engineer. But I can try answering that question. There are optimization algorithms and there are search algorithms that have, as I mentioned, very wide applicability. So if you look around, I'm sure you will run into papers that mention climate modeling and other things. It's a very active field. People look for quantum problems. They are very hard to find based on what I hear from our theorist colleagues, that you have to look for certain structures in the problems which make them suitable for a quantum computer. But I believe there is still a wide range of applicability. Another point I can make that is related perhaps to your question is that beyond this question of how fast the algorithm runs to find the solution, there is the problem of loading your problem or your data into a quantum computer and reading out the outcome of it. We have these prototypical systems with maybe hundreds of qubits, but they still operate way slower compared to the gigahertz rate of our conventional phones or computers. So this problem of loading data and unloading data actually is a very important one. It turns out that most of the current research is on type of problems that involves very hard computation on relatively small sized data. What would it map to in practice? It's honestly beyond what I know.
Looking at your linear channels, thinking about classical computing and pipeline processing, are you able to clock all the qubits, like say 20 qubits, can you clock them all one to the right, two to the right, that type of thing, and so you can have some geometric ways to do your entanglements that are only located here and there throughout these.
Is this about the directional?
Mostly appear to focus on the linear aspect of where you're at right now. Is if you think where you're at, you could actually move a loaded state and more efficiently just move everything to the right, say, two positions.
Yeah, so the question is, I believe, the question is about what happens in a linear system where everything is talking via a single channel. So the unidirectional information or state propagation has a couple of implications. One of them is that if you have frequency control over your qubits, you can single out a pair and have them only talk to each other and not anything else. There, one qubit can launch a state and the other can just receive it. In principle, with 100% efficiency, the process of emission is the time-reversed process of absorption. So you can do it if you have control over directional, what we call directional coupling to the qubit. But there is more complicated schemes too, where you actually start with sending photons into these unidirectional channels, and then you let the system continuously absorb photons and emit them. And it turns out that with well-chosen parameters, you can actually force qubit pairs or even multiple qubits to settle into an entangled state. That is what we call a dark state. The system naturally evolves to this state, and that is where it would be essentially decoupled from the rest of the world, which is another way that has been in theory proposed for using these type of channels. So I believe the question is, what are the hardware aspects of things that we need to change to get to practical applications for these type of systems. I mentioned some vague ideas. The number of qubits was one of them. It turns out, though, that just increasing the number of qubits is not all you need. If your qubits are not good, namely they decohere a lot during the time you need to do operations on them, a very large system becomes relatively useless. You essentially get all the quantum states scrambled too soon, and you cannot move a state from one part of the system into the other one. So one key metric is this, what we call as the fidelity of quantum gates, which essentially is this competition between decoherence and how fast we can do operations on the qubit. What is needed to get better fidelity or better qubits quickly becomes platform dependent. I talked about superconducting qubits, but there are different things like atoms or solid state qubits out there. For superconducting qubits, the challenges of making a better qubit or a higher fidelity qubit is mostly in the material science. It turns out that decoherence is set by defects in materials that can essentially absorb some of the energy or create dephasing in our system. So making better materials and better interfaces seems to be a big part of what is needed to make better qubits.
What are the power dissipation of these kind of transducers for operating at low Kelvin temperatures?
Yeah, thank you. That's an excellent question. The question is, what is the power dissipation of these transducers? So obviously, power dissipation is very important. Let me go to my slide, if I can get there soon enough. Yeah, these dilution refrigerators that these experiments are done at have a very small cooling power. At a low temperature, a typical number is tens of microwatts. So it's very important not to dissipate too much power in the process of conversion. Most of the dissipated power in the experiment that I described comes from absorption of the laser light in the device. And if you calculate the numbers, the amount of energy dissipated to convert a single qubit or a single quantum state of a qubit is on the order of 10 femtojoules per qubit, which is not a large number, which means that you can still put many of them in principle in a fridge. However, even though this heating is not causing problems for our cryogenic instruments, they do cause a lot of problems for the devices themselves. The signal to noise ratio that I mentioned, I didn't tell you where the noise comes from. It turns out that the noise is primarily coming from this little bit of absorption that still exists. So, some of the research is actually on pinpointing where is this absorption happening, how to reduce it, and the rest. Excellent question. Yeah, the question is, well, the first part of the question is, why is this y-axis so low, I presume? And the second part is, with these low efficiencies, what can you do with this system? With a part also asking, is detecting photons all you need? So about these values, yes, these are the probabilities of detection. If you were to break down these 10 to minus 5 numbers, about 2 orders of magnitude is in our measurement instrument. So we have to do filtering on these optical photons and many other things, which in this particular experiment were not optimized. So they are technical and can be improved. That leaves you a number of about 10 to minus 3, which has been improved since this measurement from a couple of years ago, but it's more or less near the state of the art still that you can work with. Now, this is still a low efficiency. For directly transmitting quantum information over a channel, which is what I explained, this would be a total killer. You cannot do it. But there's other protocols for quantum information transfer, namely teleportation, where you start with a pair of entangled photons at 2 sides, and then you use them to erase a quantum state and create another one at the same time. For these type of protocols, we do what we call heralding. Essentially, you try many times to make entanglement, and then if you succeed once, that's all you need to do. Then it's a question of the rate. Can you do the experiment fast enough And then you can translate these efficiencies into entanglement generation rates. The rates with current systems are in the lower ballparks of a kilohertz for entanglement generation, with optimizing everything, which is not useless. It still can be done for 2 nodes experiments, for example. But again, a lot of research is in increasing this number. And to answer the second part of your question, you need to also show the preservation of phase in this process. This is a detection of the chance of getting a photon. Phase preserving measurements have done since this one that I mentioned. There's also other reasons to believe this process is phase preserving. For example, there are previous experiments with only phonons and optical photons without qubits, which use similar type of devices. So we know, I would say, enough about these systems to be confident that they preserve the phase, but nevertheless, that also needs to be seen in action, I would say. Okay, well, thank you once more. I hope you have a good rest of the day.